So looking at this problem, the goal is to figure out the F-test statistic, which is what we want to use for our one-way ANOVA. In the calculation, it's a ratio. On top is the mean squares of the treatment, and you divide by the mean squares of the error. And the mean squares of the treatment, you're going to take, so there's all the different samples. And I can tell you in this problem, there's 5 samples because our degrees of freedom for the treatment is 4. It's always one less than the sample size. So in ANOVA, there's always at least 3 samples. In this one, we have 5 samples. So the mean square of the treatment, you would take the mean of each sample, minus it from the overall mean if you combined all the data together. And you can see the exact formula on page 626 in the book. Basically, you're squaring that, weighting it by how many are in each sample, and then dividing by the degrees of freedom. That's what this formula is right here. They've done all the legwork for us. The sum of the squares is right here, where they take the mean from each sample and subtract the overall mean and square it. They've done that. It's 537, and we need to divide by 4. That's what MST is going to be on top. And so another way to think of that top part is between samples variability, because we're looking at, and this is illustrated on page 625. We're comparing each individual sample to the overall mean, so we're kind of seeing the differences between the samples. But while on bottom, the mean squares of our error is within each sample's variability. And the calculation for that is we're just going to look at the variance from each of our samples. In this case, we had 5. And the formula on page 626, you take that variance, you multiply it by 1 less than the sample size. We're going to add all those up, and then we're going to divide by the total number of data objects there were, total sample size, subtracting how many samples there are. So again, the legwork's all done here. They've done all that formula here. When we square all our variances, multiply them by 1 less than the sample size, we get this value. And if we take our total number of data pieces, our total sample minus how many samples we had, we get 29. So this one, we're just going to divide that number by that, and that goes on bottom. And then we're going to need that ratio. So you can see that's how we're solving this problem. We do 537 divided by 4. That's our top number. 5 through 20 divided by 29. That's our bottom number. And then we just need to take that ratio. And so when we do that, we get 0.732, and that is our F-test statistic that we use for our one-way ANOVA. And basically, the summary of how to interpret that is the larger it is, it means the top number has to be bigger than the bottom number. Think about division. The bigger the top number is, the larger your F-test statistic will be. And the larger we have, we take it as evidence against the null hypothesis, which for ANOVA, the null is always that every single population has an equal mean. So that's where we assume all our populations are the same. If we get a really large answer back, which this is not large, this is less than 1, but if we got a really large answer back, we would assume, okay, probably one of the populations was different than the other. And that's how we use the F-test statistic.